Oh, Simon, what did you do this time?
What do you mean?
You're glowing.
What?
Perfect, Simon. You just introduced the class to radiation. Today we are going to talk about radionuclides.
Are you suggesting we talk about chemicals where the nucleus of the atom is unstable?
Well, of course I am, Rin. That means we're going to take an adventure to the Engel lab.
Wait, does the Engel lab have anything to do with me being green?
Sure it does. We could see what atoms are making you green.
And here we go.
I think I'm gonna be sick.
It's a field trip.
Seatbelts, everyone!
Please let this be a normal project.
With Dr. V? No way!
Cruising on down State Street, you're relaxed and feeling good. Next thing that you know, you're seeing
Badger in the neighborhood!
surfing on a new glide, swinging through the Tron. Take a left at your isotope, take a right at a neutron on the Magic 80. Fly by the Magic 80.
Spank a proton, too.
Out of Magic 80.
Wrapped a river of acid.
On the Magic 80.
Such a fine thing to do.
Strap your electron to the seat. Come on in and don't be shy. Just to make your day complete, you might get contest to what am I on the Magic 80. Ride the ride, come on. Ride on the Magic 80.
Okay, everybody, this giant picture is the table of the nuclides. Everything you see in black is a stable, everyday element. The boxes in blue represent nuclides with too many neutrons and not enough protons. Those are unstable. And the pink represents nuclides with too many protons and not enough neutrons. Also unstable. When a nucleus is unstable, it knows what it has to do to fix itself and get back to a stable form by changing its structure. Sometimes this means it shoots out an electron, other times a positron, or maybe even a really big alpha particle, which is just a fancy way of saying a helium nucleus.
Where are we?
We're in a giant machine, duh.
Actually, we're in a big machine called a cyclotron.
What does the cyclotron do?
Well, imagine we're a little atom and we want to get excited. We're about to find out what happens next.
Whoa! It's getting really hot in here. That wasn't very exciting.
No, Simon. Look, it was exciting.
Exactly! We just added protons to a piece of iron. We're lucky. 99% of the protons that come out of the cyclotron get lost to the environment as heat.
So we became a different element.
Yes, since we added a proton to the iron 54, it shot out some of those alpha particles and became manganese 51, which has a charge of +2. Now that we're manganese, we need to be filtered out using something called extraction chromatography. That's when they use something called a resin, which attracts certain particles but not others, as well as different kinds of acids to separate the components of a solution.
That was fun, but what do we do now that we're stuck in a bunch of acid?
I'm not sure, but all of the water is leaving.
We're drying!
Please, no more.
One more step of dissolving and we will finally reach our destination.
Wait, what kind of water are we in now? It's salty.
Well, Annika, that's because it is. We're in a special solution called phosphate buffered saline, or PBS. It's special because when they put it inside our blood, its composition allows it to mimic our blood. And many of the ingredients in PBS are different kinds of salts.
Are we inside the mouse?
To be exact, we are in a voltage-gated calcium channel. They are found in the nerves and are gated to make sure that only calcium ions can get through. However, manganese is similar enough to calcium that it can mimic it in the body. This is because they both have the same charge thanks to the number of protons and electrons. Since their structure is similar, they can play similar roles in our nerve cells.
But why are we in the voltagulated calcium?
We're in the voltage-gated calcium channel because the scientists in this lab want to study the pain reception of the mouse. These channels, being in the nerves, are active when the mouse feels pain, and calcium controls when nerves send pain signals. So because manganese mimics calcium...
Whatever this manganese ion does, a calcium atom would do the same thing.
And because the ions are radioactive,
The scientists can see them in scans.
So if we put these ions in me, we could figure out why my stomach is hurting?
If we scanned your body for radioactivity, yes, we could.
But wouldn't that hurt him to have radioactive particles running around his body?
Actually, he'd be just fine. The ions in saline solution have to go through several quality control metrics before they are injected into any organism, whether it's a mouse or Simon. Well, I hope you all enjoyed our little field trip today and learned something from it, because there is a lot that goes into using something like radioactivity in medicine, and we only saw one of the many, many ways they can apply it. Right now, in just that lab, there are multiple projects that take those little radioactive nuclides and do all sorts of different things.
I, for one, never want to be glowing again. But I did like going down that big water slide thing.
And I thought it was really cool how we changed that iron disc into manganese.
I want to know more about how they can make so many different radioactive nuclides.
I just never want to go on that cyclotron thing again. We went in so many circles so fast I got dizzy.
Oh, William.